So in general, the tolerance value for M8 fasteners will not be available, but for our case, we will take it as like plus or minus 0.1. Okay. So since it is plus or minus 0.1, I'm going to convert into off value. Okay. So now we got the variation for the dimension number A. Then we come to the axis of this hole. Okay, and then we are moving back to the next hole axis. So here the variation is 120, the nominal, and the variation is 0.5 position tolerance. And the dimension we are talking about is 120. The variation is position tolerance of 0.5. So which is nothing but plus or minus 0.25. So I'm directly entering 0.25. Okay, now we are at this axis. From this axis, we are going to the next dimension, which is C. Okay, so again we see a fastener. Pardon me if the spelling of the fastener is wrong. So here also we are dealing with the size of it, and then the direction is positive. And then as we know, the size of the fastener is 5, and the variation is plus or minus 0.1. I'm going to give the same value. Okay. From there, we are again moved to an left end of this surface, which is where the part transfer happens, and then from there we are going to the axis of the hole. So the value here is the direction is negative, and then the size of the hole is 12 plus or minus 0.5. So we need to 12 by 2. So plus or minus 0.5. You need to give 0.5. So I think same we need to apply over here. Okay. So we are the axis of this hole, blue color part. From there we are going to axis of the next hole, and then this is the location tolerance of it. And then the sign is negative, and then the nominal value is 120. So the variation is similar to the. Okay. So now we are at the axis of the hole. Next is we are going to the end of our measurement feature. Okay, positive, and then the whole size is similar to what we entered earlier. So that's all. So now our tolerance stack up loop is completed, and then we populated all the tolerance into the tables over here. So we start at the left of the gap, and then we ended at the right of the gap. Okay, so now we included all the tolerance which are included in the system. Okay, now let's see the output of it. So now here it says that WC variation, this is worst case variation. Okay, so the worst case variation is plus or minus 1.1. It says that it can this surface can go it can get interference of around 1.1, and then it can get a gap of around 1.1. so that is what this whole worst case results are telling. So from this we come to know that our system is failing, so the part cannot be fixed if the tolerance are at its worst case condition. Okay, so it doesn't necessary that whatever the manufactured parts is always at its worst case. It can be anywhere between in its range, as I explained earlier. It doesn't mean that it should be only fall around this range. It can fall anywhere over here. Okay, so that is where the statistical analysis comes. So this is an RSS analysis, RSS results. So RSS is nothing but the root sum square of all the variables we are dealing with. So this will assume that all the processes are in control, and then it tries to take all the variations towards its mean. So in RSS value, our variation is plus or minus 0.5. So here the chances is that more chances that the part will get fit, so that we won't see any interference up to 1.1. You see only an interference of 0.5. So if you see an interference of 0.5, then let's come to the solution. So our objective is to make sure the part get assembled. So either way, one is we can increase the hole size or reduce the tolerance or make some manual adjustment in the assembly and then assemble the part. Okay, so these are three solutions we got here. Since it's a 1D tolerance stack, the procedure says that we need to bias the whole part to one side and then wait to take the measurement. But if you try to assemble this in practical, if you see some interference, you can move the part towards right and then assemble. So that if the manual adjustment is possible, then it's easy to solve the solution. But we need to know how far it can be adjusted manually. So let's say the nominal gap of it. So the hole is 12 and then the fastener is 10. So we see a nominal gap of 1 millimeter, right? 12 minus 10 by 2. So the radial gap will be 1 at nominally. So when the parts are at nominal, the operator can adjust this whole system, the flange, and then he can assemble. That is one solution we got here. The next solution is if it says that it is a robotic assembly and then there is no point of adjusting the part, then we need to give a different solution. Is that either we can increase the hole size or we can reduce the tolerance of it. So let's say instead of 12, let's say our hole size is around 30. So we got a clearance of around 2 millimeters. I'm sorry, 1.5 I think. So that will one way solve the problem. And next is we can reduce the overall tolerance over here. Let's go back to this presentation and then so these are all the 5 steps to do a 1D tolerance stack up analysis. Next is let's talk about the pros and cons of this analysis. So here it's a simple tool. Within a little bit effort, we can come to know what are the variations, or we can do a tolerance analysis, and then so this will works for very small assemblies and then simple objectives like I showed over here. But and there are variables. If you have like a part of a 15 gap, then it's not fixed. Okay, that's what. There are a lot of assumptions we did over here. The assumptions we did in this case is we assume that these fasteners are like straight and then the holes are all straight. So what happens when the whole feature fastener moves something like this? The whole fastener can tilt within its tolerance range, and then this hole can also tilt in its range. So these are all some of the factors we eliminated in this analysis. Okay, as I said, it won't work for complex assemblies. So these are the pros and cons of the 1D stack up. So next we are going to take as another simple example of 2D tolerance analysis. It's like predominantly this was like it is not performed or advisable to take a 2D analysis because we need to take a lot of assumptions and then it may go like end up in an error. But I'm going to give a simple example and a simple demo how a 2D tolerance analysis to be done. Okay, so here as I said we are dealing with 2 variables. Let's say we have a small insert like a poke feature, going to put it in this base part. Okay, so if this gap be assembled, okay, so we are going to check this variation, the gap of this slotted in this feature. So here the problem here we face is it's like an inclined feature. So the variation will come from horizontal movement of this whole insert and then the vertical movement of the whole insert. Okay, so that's why we resolve both the Tx and Ty component of the objective and Ty component of the variable. So I'm directly going to this tool, which I'm going to show a demo for the 2D stack-up analysis. So first in 2D data stack-up, we need to convert all the variables into a horizontal and vertical uh, variations. Okay, let's go to this drawing. Let's study this drawing first. Okay, so this is our base part, which have like an this datum A, B, and C, and then we have like a pin of size 10 plus or minus 0.5, and then we have these two surfaces we are interested in, which is having a profile tolerance of 0.5. Okay, and then come back to this insert. They defined a profile tolerance of 1 with respect to ABC. These are all the corresponding datums, and then we have a hole which is having a size of 11 plus or minus. Now the problem we see is with our tool we can either do an axial stack or a radial stack, right? Okay, let's take this. We have a provision in our tool. We have provision to measure either this direction or this direction. So what we are trying to do dy components, and then we are going to check the variations individually and then combining these two variations at the end. Okay, we already prepared the stack loop for this, so I converted all the variations into horizontal. Okay, so for this, the drawing we may not have this all the dimensions which are interested in the stack. So I just prepared those dimensions. Let's take this. So it's very simple. From the axis datum B, the this vertical also. So from nominal we have an angular surface of 28.15, but we need a tx and ty component of it. So we need to do a small trigonometric calculation and find 60 horizontal and vertical component, or simply we can measure the point in the CAD tool we are using. Okay, so I just measured the kind of nominal values, and then for simplicity I just populated over here. So 16.78 and 23.02 was the horizontal and vertical tolerance of this particular point. Okay, then move back to this. So from this I'm going to do a regular stack up analysis. So here the dimension is A, and then the component is base part, and the description is measurement surface, and then the stack loop, it's in the positive direction. I'm going to give a positive direction, and the mean is, as I mentioned, I already kept over here, that is 23.91, and then the variation is plus or minus 0.25, which is a profile of 0.5. Okay, so the next is we went to the datum B axis. Okay, from this datum B, we are going to bias it on the right side so that we get a minimum gap over here, and so that value is, so we need to do is 10 by 2 because it's an radial system. Okay, so the size is 0.5, so we need to take. So next is the dimension C. Now we touch the pin, and the hole got biased over here, so the part transformation happens, and then we move to the next part. Okay, so next part is the insert, and then here is the hole size, and then the sign is negative, and then the hole size is, I hope it's 11, and then the value is similar to we see in the size of the pin. Okay, now we are at the axis of the insert axis of the hole of the insert part. Now we are going to the measurement edge of the measurement surface, and then the sign is negative, and then the value is, since for simplicity I could put over here, is 23.02. Okay, so here next is the interesting part of it. So the whole surface, the profile tolerance is applied to is of 1 mm with respect to the inclined surface, right? Let's just concentrate on this only, the insert, right? So the tolerance zone is, this part can go anywhere in this surface, right? But the problem is, we need to know the tx and ty component of it. So I need to know if this is your surface, and then this is your tolerance range. I need to know how much it can go in horizontal, and then how much it can go in vertical. Okay, so that's why a small trigonometric calculation we need to do to get the variation of it. Okay, so we knew the hypotenuse of it. We need to find out the opposite and adjacent variations. Okay, and then we know the angle of it. Okay, so I added one more column over here. So the our hypotenuse variation is 1 millimeters, and then the angle we are interested is, angle of the slope is like 40 degree. Okay, now we come to know that the variation is 0.7 at the opposite side and adjacent. Since it is like in 45 degree and a right angle triangle, the opposite and hypotenuse are same. Okay, now I need to give this overall value. So here our range is 0.707 by 2. So now the stack loop completed. So now we started from the left side, interested the surface of this brown color part, and then we come back to the edge of the insert. Okay, now let's see the worst case variation. The worst case variation is 1.1 mils plus or minus. So our mean is like 0.39. Okay, I hope there was nominal numbers. So yeah, I forgot to update here the nominal CAD nominal number. What I got is like 0.887. Okay, let's take this lowest picker 0. Okay, now can you see this mean shift is 0.5? That 0.5 is because we shifted the whole part to the left side, so this gap will get reduced in the loop. Okay, so our mean is 0.39, and then our worst case minimum is something around negative 0.17. Okay, so this is an issue. So if part moves only in horizontal direction, it's going to see an interference of 0.7. Okay, 0.117. Okay, so similarly I already performed an vertical stack for this. So I'm going to show this over here. So here I did the same calculation, and then I put all the nominals, and then I end up with a gap over here. So our nominal is 0.88, and the mean is 0.37, which is similar to the earlier one because it's like our right angle triangle is like 45 degree. So on the similar variation we got. Okay, now the step what we need to do is, we know the horizontal variation and we know the vertical variation. Okay, so and then we need to calculate the uh, hypotenuse over here. So for this I have this resultant calculation. If you put all these variations, so the variation is 0.17, and then the variation over here is 0.13. It's like similar, like both the same value. Let's put over here, and then we got like an resultant value of 1. So in the slope, in the direction of the slope, the part can move, interfere up to 1 millimeters. So that is what the stack is telling. Okay, this is how we can resolve the objectives, and we can find the variations for these kind of applications. Okay. Okay, so next is the 3D tolerance analysis. So I'm going to just give a glimpse, since like we are running out of time. I'm going to give a basic example what 3D analysis, and then what are its advantages and some simple methodologies. Okay, so to do in manually it is very complex, so we have like an readily available softwares in the market, and then we can use those to do a tolerance analysis. So these are like an specialized skilled engineers we need, so we should be like what I meant to say is like these are special tools which in it's like available in market, and then if we have like enough skills, we have a huge scope. So I just show some of the 3D analysis tools. We have the 3D CS, this VSA, CTAL, Six Sigma, CTAL, Six Sigma, and so on. Okay, so here also I just as I mentioned the two basic methodologies, these 3D analysis softwares used. Okay, so here the feature based modeling. The feature based modeling is such that each and every feature will be defined. For example, a point, a plane, a whole slot will be have like an predefined in the software, and then they have a predefined degrees of freedom and then constraint to it. If you take an whole, so it have like an 4 degrees which can be controlled like tx, ty, rx, ry. So these are all predefined in the software, and then we can use this features to build our model. So most of the case it will be like CAD based model, so you don't need to worry about. If you select the CAD features, you can build the model without any issues. The next is the point based. So point based is each and every variable in your assembly will be converted into a point. Okay, so point for example point or line. So if you take a line element, it have like in 2 points. So each and every point will have its own vector and magnitude. So by defining these variables, you need to build the model so that the variation will be calculated. Okay, so whatever the even these point based softwares have like a feature modeling system, where if you select the feature, it converts the selected feature into an system that the software understands. If you select a planar feature, it converts that plane into an n number of point and line system, so that the software can understand. Okay, so the example for point based system is like this VSA and 3DCS. So feature based is like CTAL, Six Sigma, which is like have a feature based modeling.